Hello everyone. Today I'm going to present my mini project titled Anomaly Detection in Network Traffic using Isolation Forest and Autoencoder. This project is basically designed as a full stack system with a front end for user interaction, a back end for processing, and a machine learning algorithm for anomaly detection. Introduction, like in today's digital era, cybersecurity has become a major concern. Networks are constantly under attack, and intrusion detection plays a critical role in ensuring data safety. So, traditional methods of intrusion detection are mostly signature based. This means that they can only detect known attacks, but they fail when new or unknown pattern appears. So our project overcomes this by using anomaly detection techniques that can be automatically flag unused traffic patterns, even if they have ever been seen before. So yeah. So the motivation for this project comes from the increasing number of cyber attacks worldwide. Manual monitoring of network log is both time consuming and error prone. By combining machine learning and deep learning into a simple web application, we make intrusion detection. It's easy to use, more automated, and more reliable. This project not only demonstrates how ML or DL can be applied to cybersecurity, but also shows how to integrate them into a user-friendly or full-stack application. So yeah, so let's understand what is isolation forest. Isolation forest is basically a unsupervised machine learning algorithm. The idea is simple. The anomalies are rare and different from normal points, so they are easier to isolate. It randomly splits features to build trees. Formal points usually need more splits to isolate, while anomalies can be separated in fewer splits. The advantages of isolation forest are it is fast and efficient on large sets. It does not require label data. In this project, isolation forest outputs whether each record is a normal or anomaly. So the second algorithm is autoencoder. Autoencoder is a type of neural network used for anomaly detection. It has an encoder that compresses the input and a decoder that reconstructs it. The model learns to reconstruct only normal patterns during training. When we input anomalies, the reconstruction error becomes high because the network has not learned those patterns. So by settling a threshold on reconstruction error, in our case, it's 95%, we can easily classify data as normal or anomaly. This makes autoencoder powerful for capturing nonlinear and complex pattern in data. So both algorithms have their strengths, like isolation forest is statistical and tree-based, good for fast anomaly detection. Autoencoder is deep learning based, good at learning hidden patterns. By combining both, our system becomes more robust and reliable. If both models agree, the result is very confident. If they disagree, it indicates a data point that need closer inspection by a security analyst. So now let's look to the demonstration of the project. So we'll run the project using Python .py. It will run on the localhost 5000. So we'll wait for its running. So yes, this is my home page. We have two options here that we can run a demo sample data. It basically generates the sample data and run it. And also we have an option like we can upload any data set. So I have one data set, so I will upload it. Okay, so this is the test data set which we will use. Okay, it's analyzing. So as you can see, there are total 600 records, from which 2028 are predicted from isolation forest and 30 are predicted from autoencoder. So you can see two visualizations. Basically, this is just to compare the anomalies that is detected by isolation forest and detected by autoencoder. The histogram here is basically we have on x-axis we have reconstruction error, which is the mean square error between input data and the autoencoder output. And on y-axis we have frequency. So the histogram shows well the autoencoder is reconstructing the data. So yeah, so most normal traffic falls on the left with lower error. We set a threshold at 75% percentile, shows as a red dashed line, which is this. And any point that crosses this line is considered as an anomaly. So the bars on the right side of the red line represent anomalous network activities. So, okay, so this is the display of the data. Here you can see that this data is predicted from isolation forest as anomaly, and for at autoencoder it is normal. So the data which are predicted as anomaly for both these algorithms are pure anomalies, and which are not or can maybe again analyzed by the cyber security analyst. So yeah. Also, we can download the result file. Also, here also we can analyze another file. So we'll just download the file and I will show you. So this is the .csv file. Okay, okay. See, we can see the data we were seeing on the user interface. We can see it here now. Okay, so now I will show you this data set. So you can see this is the data set we have entered as an input. So let's start with the code. This is the train and export file. Instead of training models every time the app runs, I train them once here and save them in the model folder, which is this. So yeah, okay. Here I defined some settings. The folder where the model will be saved, and whether to use PCA PCA or not, and how much variance to keep. Like here I have keep 95% variance. PCA basically helps to reduce dimensionality and makes the autoencoder lighter. Okay, then I have loaded the data set for training. This is basically the training data set. Uh, okay, basically in this block, I loaded the data set, and I can either use a real data set like NSL-KDD generate generate a synthetic data set using this create sample network function. This function basically it simulates normal and anomalous traffic by tweaking features like duration, source byte, and error rate. It also labels some rows as anomaly for reference. Yeah, we return the DF here. Okay, so this is the encode categoricals. Since machine learning models don't understand text like TCP or HTTP, I'll use label encoder to convert categorical columns like protocol, type, service, and flag into numerical codes. I also set this encoder so the Flask app can correctly transform new incoming data. So, okay, build feature matrix. So here I drop the label column if it exists because isolation forest and autoencoder are both unsupervised models. They do not need label for training. The rest of the column becomes our feature matrix. And this is scale. So next, I scale all numerical features using standard scaler so that they are on the same scale, which helps both algorithms. If PCA is enabled, it reduces the dimensionality while keeping 95% variance. This makes training faster and avoid noise. So here I have trained the models like the isolation forest. It is basically a tree-based algorithm that isolates anomaly with fewer states. So yeah, here I have 100 estimators and contamination is set to 15%. And for autoencoder, if the okay, where it is. Uh, okay, for autoencoder, I have trained it for 20 approaches and with the MAC loss. So here I have saved the artifacts. Finally, I have saved everything into the model folder. Like this, you can see here the autoencoder.h5 best isolation forest PLK features name label encoder PCA scalar. So yeah, this is the training and explore.py. Now we'll understand what is app.py. Okay, so this is my app.py. I'll start at the top. We imported Flask for the web server and templating, Pandas or NumPy for data work, Scikit-learn and TensorFlow for the model, Matplotlib for chart, and a few utilities like OS and job.lib for saving and loading artifacts. Then I created the Flask app, set a secret key specifically and upload folder and a 16 MB max file size. I also make sure the upload and the models directory exists so the app never fails due to missing folders. So next I define global variables to hold everything in memory. The isolation forest, the autoencoder, the scaler, optional PCA, the label encoder for categorical columns, and the feature name list. Keeping this as global means we load them once and reuse them across requests, which is fast and avoid reinitialization. So this is the function. This helper function creates sample network data, synthesis realistic network traffic. It actually creates categorical fields like protocol type, service, flag, and numerical features like byte, counts, and error rates. I also inject a controlled fraction of anomalies by pushing certain values to extreme ranges. This powers the root demo so we can demonstrate the app even without a real dataset. So this is the train models function. If the app can't find safe models, it basically uses this train models to train a small demo set so we can keep going. The training flow is like the first label encode the categoricals like protocol type, service, and flag. And second, it scales all features with standard scaler. Third, it trains isolation forest for unsupervised anomaly detection. Fourth, it trains a dense autoencoder to construct inputs. Anomalies will later show high reconstruction error. Fifth, it save all artifacts into the models folder. The isolation forest model, the autoencoder model, the scaler, the encoder, and the feature list. So in production, I prefer a separate training script to keep the server light, but this fallback makes the app self-contained for demos. Then it's the load model. On startup, for the first time, we need models. We call the load models. This function checks that all required file exists. That is the isolation forest file, autoencoder, scalar, feature names, and the label encoder. Important details here is I load the autoencoder with compile is equal to false. The I did that because it avoids common Keras serialization error between the environment. Okay, if PCA was saved, we load it, otherwise we process without it. And finally, I run a sanity check, and if anything messes or corrupt, I retrain and reload, so the app always end up with a valid model set. So yeah, for safeguards, I have model ready and ensure model loaded. Before any root uses the model, I call the ensure model loaded to check if the model aren't loaded yet. It triggers the load models. If model fails, we stop early with a clear error. This also avoids non-type crashes, especially when Flask debugging the loader runs code twice. So this is the preprocessing data function. This function mirrors the training pipeline exactly, which is crucial for correct prediction. Here's what it does is that first the label encode the three categorical column using the save encoder. If a value wasn't seen in training, I map it to 0 as a safe callback. Second, it makes sure all expected features column exist and are in the same order as during training. Third, apply the save scalar, and if PCA is present, apply PCA2. It returns two things. Process DF, that is the clean data frame we can show in the UI, and scale data, the actual numeric matrix feed into the model. So if you ever seen weird result, it usually because inference doesn't match training. Saving and reusing this exact preprocessing object prevents that. So next is the make result plot function. This small helper produces the two charts we show on the result page in one go. A bar chart of anomaly count for both model and a histogram of the autoencoder reconstruction error with a red threshold line at the 95th percentile. I return the figure as a base 64 PNG, so it's easily to embed it in the HTML template. So these are the roots. First is the home root, the index root. This basically renders the home page. So this is the upload route. In this route, basically, I first call ensure model loaded. Then I validate the file type and save it into the upload directory. And if it's CSV, I read it with headers. For TXT, I read it and align column if headers are missing. Then I call preprocessing data to encode scale and optionally apply PCA. With the scale data ready, I run both models. That is the isolation forest. It runs -1 for anomaly and 1 for normal. I map those to strings. Then the autoencoder produces reconstructions. I compute the MAC per row, then sets the threshold at the 95th percentile of the MAC. Anything above it is an anomaly. I then build a result DF with original feature, both the prediction and the reconstruction error. I save it as upload slash result.csv file. Finally, I call the make result plot to generate the chart and render the result page with the preview table, count, and the plot. So yeah, we have the third route, that is the demo route. The demo route basically creates synthetic data, runs the same pipeline, saves demo result.csv, and renders the same result template. This is perfect when you want to demonstrate the app without hunting for a dataset. Fourth, I have the download route. This route returns upload result.csv as a download, that is the CSV file as a download, so that the user can analyze the predication offline. Then fifth, I have the API predict. This is the REST endpoint. This is a JSON API for single record inference. It accepts the JSON object, preprocess it the same way, and returns the isolation forest prediction as normal or anomaly. This is useful if you want to integrate the detectors into another system or call it from Postman. The sixth is the API health. This is a tiny little health check that reports whether the model are loaded and whether PCA is present or not. And yeah, this is the entry point. At the bottom, I call load model once before starting Flask on port 5000 while debugging is equal to true. Flask autoencoder might initialize twice. The redness guard prevent any non-type error. So yeah, this was the app.py.
So I would like to conclude the video. So basically, we develop a full stack intrusion detection system with Flask and HTML as front end, Python as the backend, and machine learning algorithm, the isolation forest, and the deep learning algorithm, the autoencoder. So the system is easy to use, provide visual insights, and support CSV download and REST API endpoint. For future improvement, we can train the model on real world datasets like the NSL-KDD or use live packet capture. We can also deploy a system on the cloud using Docker or Kubernetes, and also we can extend it to streaming data or real-time intrusion detection. So this project demonstrates how ML can be practically applied in cybersecurity. So hope you like this video. If you liked it, press the like button, also share and subscribe to the channel. Thank you.